Hello, hello. It is time for lecture 19, 5, 10, 15, 19. Yes, 19, 1, 9, 9, something like that. Yes, lecture 19 is very excellent because we are now transitioning from what we knew about electricity and magnetism and noise and music and sound and all that good stuff. And now we are going into the realm of quantum physics. Ooh, and then from there, that natural connection between quantum physics. Yeah, you're like quantum physics. No, but really, it's quantum physics, real reality, the way the universe works. Quantum physics knits together with atomic physics. Remember earlier in the semester, we talked about the Rutherford atom and things like that, right? And now we're going further. Then you knit them together to understand cosmic physics, the physics of the universe itself, and how we came to be and how everything came to be what it is today. It is pretty amazing stuff. And I wish we had an entire semester, an entire year to go over the details of this cool stuff. In some classes you actually do, but alas, in this class there is not. We're just going to skim the surface and show some of the highlights of the best stuff. Lucky you, we get to hear about the cool stuff, about the rest of like the grand picture of physics. Wow, so much to talk about. So let's get right to it. Okay, remember, from we've been doing up to this point, right? We figured out why things move, and you have Newton's laws of motion early on. Then realize, wow, the motion of things, right, requires something called energy. Then realize that energy isn't just about things that are moving, but they're also hidden in the motions of objects, little things moving around. Realize, wow, there's lots of little objects that put us all together, right? Not just like atoms, but within them, the standard model, things like quarks and leptons and bosons and photons and electrons, which are respectively a boson and a fermion, all kinds of great stuff. And throwing them all together, realize, wow, at least some of those little tiny particles have lives of their own. And they do things like the photon, right, which turns out to be a particle and a wave at the same time. And then from there, you see, oh, there's electromagnetic radiation and waves and all that. And then realize, oh, well, that whole thing about electromagnetic radiation means that like the radiation, first of all, travels in waves. So for example, the reason we hear each other is because of sound waves. The reason we see each other is because of light waves. But these things are not just waves, they're also particles, these photon things, right? And not only are the things that are carrying that force, electromagnetic force, right? That's photons. The actual electrons themselves that actually move around, they can do work, they can create forces. And then you learned about electricity and magnetism. And when you have electric charges moving, you create magnetism, magnetic stuff. We're playing with those things. This is too much fun. There is so much connection to the whole thing about physics. It's great. The connections, of course, not just with how things work, but our whole world itself, our lives, the things that we do, the things that we decide about how we live or how we do public policy or organize our society or behave on a daily basis. All of that physics informs, and being understanding about all those connections gives you tremendous power and authority and ability to make good decisions about things that literally can make you rich and healthy and happy and things like that, right? Yeah, that's where we are at this point in physics, right? So therein lies that transition point. That electron, the particle, and then the photon, that particle, which also travels in waves. And what happened was, starting around the early 1900s, people realized that electrons were waves too. Are you kidding me? Yes. And those particles that move around and carry electricity, right, create current by moving from one place to another, that trigger electromagnetic forces to be usable. Those are particles, right? Those electrons. Well, it turns out that they're waves too. In fact, that understanding that there's both particles and waves for every little thing, right, is the core of quantum physics. So let's get right to it about that quantum physics thing and go in that direction. All right. I will refer you for fun, okay, although you don't have to do too much of it in there, but I want you to read the quantum physics section, chapter 29, okay, of the OpenStax College Physics textbook. There's good stuff in here, and it sort of explains an introduction to what quantum physics is all about. We'll talk about it in this class. I'm not going to do this, like read the whole textbook for you, because that's not a good use of your time, right? But at the same time, I can give you the highlights of the cool stuff that you should read and been doing in your study guides. I hope you're filling out your study guide as we speak, in order to feed right. Now, this is like, ooh, it's a fly. It's a fly. That's not cool. I mean, this fly is harmless to human beings, okay? But look at it. The reason it seems so scary to us is because it's so unfamiliar to us. We just see black flies as little things flying around, but look at the beautiful detail. Look at the compound activity. All of that, right, is visible not because we can see it with our eyes, but because we beam electrons. We bounce electrons off of this thing, and they come back to us in patterns that we can then create pictures of. All right, that is amazing. And the idea that you can have energy, right, individual pieces of light marked as individual pieces, the quantization, right, is really quite amazing. And then that was confirmed later on, as I described earlier, with the photoelectric effect. And then we realized, oh, photons have energies. You've already done this section, the electromagnetic spectrum part. So that's not. What about photon momentum? Whoa, this thing, which has no mass, right, just energy, turns out has momentum. But wait, I thought momentum was mass times velocity. Turns out that there's this equivalence that you can eventually exploit so that even massless particles can impart momentum on objects, right? And at the quantum level, this little tiny level, you've got all this great stuff happening. And this is so amazing. Uncertainty, right? Is that actually true? The wave nature of matter, the Davis and Germer experiment is really cool. The de Broglie wave equation, and then the wave particle duality reviewed. This is some pretty cool stuff, and I encourage you to take a look at it a little bit. We're going to jump right into 29.8, the wave particle duality reviewed, because we've already talked about light, right? On quantum mechanical scale. Small particles, with or without mass, have wave properties. Both electrons and photons have wavelengths, but also behave as particles, right? This is the weird stuff that we just can't quite grasp in our heads. And so if you realize that on a rock, right, like a fist-sized rock actually has waves too, but the waves are so small in wavelength that we can't detect them. In other words, the bigger or more massive an object is, the more momentum an object can have, the smaller its wavelength becomes. And so the wavelength compared to the size of the object is tiny. You can't tell that things are shimmering. But you know what? They are, right? Oh, William Bragg, this is very sweet. To see the world in a grain of sand, and a heaven in a wild flower. Hold infinity in the palm of your hand, and eternity for an hour. Now, 200 years ago, William Blake had no idea that that had anything to do with the real world. He was just thinking sort of in a metaphysical way. Can you believe that a couple hundred years later, in these modern times, this is actual reality? You can actually have encapsulated all of the universe and stuff, depending on time and untime, and depending on how big and how small things are. Isn't that cool? All the physics, all that sort of stuff is all built in here. And I want you to realize that that is a cool concept of the universe. We're going to expound on that now, this wave particle duality thing. All right, let's go back to a previous envelope, back of the envelope type thing that I've used before for other stuff. And remember what we talked about early on as far as physics was concerned and those electromagnetic radiation things, right? We thought light was a stream of particles. That's what Isaac Newton did. That's why, for example, he was able to do optics. That's why you were able to do optics right earlier on in the semester in several of your study guide things, learning about like geometric optics and why our eyeglasses work and stuff. At the same time, though, we thought that light was a wave of energy, right? Christian Huygens around the same time as Isaac Newton was saying that sort of thing. And then with the experiments of Thomas Young, he sort of showed that, yeah, light really does work as a wave, right? Oddly, Thomas Young's experiments with the double slits, right, sending waves through, also realized, you know what, waves are like particles too. How interesting that it behaved both like waves and like particles. Hmm. So it seems like they're probably waves, right? And so James Clerk Maxwell, right, with his theories, and then later on with Heinrich Hertz, who sort of helped to evolve Maxwell's ideas into electromagnetic waves and so forth, and did worked on radio waves. And these two people, they basically showed, yes, indeed, light is waves, right? But they didn't disprove that light was not particles. People just generally thought, well, if it's light and it is waves, then it can't be particles. But actually, that's not necessarily true. Turns out that Max Planck in 1900 then sort of tried to figure out thermal radiation, like the hot radiation, the electromagnetic radiation that's coming out of hot objects, right? And from that, he figured out that, you know what? Light really is also a particle. If you treat light as a particle, the math works out. Whoa. And then Einstein, 5 years after Max Planck did this thing, further confirmed, oh yes, light must be both a particle and a wave. And the particle aspect of light was something that caused this thing called the photoelectric effect to work, where you had a relationship between how much light hit a surface and how many electrons were released. You had to add a certain amount of energy of photons in order for that to work. So it was really a long couple 100-year-old kind of story about how we got to the realization that light was both a particle and a wave. Right? Remember that? It's really quite remarkable. And so if we think about that, light as a particle and a wave, how are we supposed to sort of reconcile that with our lives? Light as a particle and a wave. And then we said electrons were also a particle and a wave. Yeah. Well, does the mind get blown? It does a little bit. But one way you can think about it is that the smaller you look, the more carefully you look at an object, the less precisely you can measure something, right? This was something that a guy named Werner Heisenberg put together. All right, let me get a back of the envelope here. And we get a marker and give this person's name a little write down here. Heisenberg. Now, Werner Heisenberg tremendously brilliant German physicist. His name shows up later, by the way. In the next couple of lectures, we're going to start talking about atomic and nuclear physics in the context of human society and what happened to us. And Heisenberg actually had a role in that. Something very interesting as we think about the history of the atomic bomb in the world. Okay, nowadays, that's like in the 1940s. It seems like a long time ago, but it's still very relevant today, as that technology from 80 years ago or so still impacts the way that we think about our society and how we organize our civilization today, right? So anyway, this guy, Werner Heisenberg, realized that for materials like atoms or molecules, or even the basics like the electron and the photon, to be both a particle and a wave, what that meant was if you focus on the wave aspect of one of the particles, then you lose the particle aspect of it. You can't measure both the particle aspect of it and the wave part aspect of it at the same time in equal effectiveness. If you say, okay, this little fuzzy thing here, this tiny, tiny little electron, okay, which is smaller than the wavelength of a single visible light photon, okay, very, very small particle, but it shimmers because it acts like a wave. If I want to think about electrons behaving as particles, I can't tell as well what the wave situation is. The more closely I look at, okay, is that particle is kind of in that location, is at that position, the less I know how much motion that particle has, right? The more carefully I measure exactly how much time there is, like at this moment of time, where is that particle? Where is that location? the less I know how much energy is in that particle. Isn't that weird? Yeah, it's like this very unusual ability for particles. Like the more you focus on one thing, the less focused other things become. All right. That became known as the Heisenberg uncertainty principle. All right. Uncertainty. What does that mean? It means that, oh man, on some level, if you go down enough looking in at stuff in the universe, at the micro scale, sooner or later, you fuzz out. You cannot get detailed enough information right at the tiniest microscopic views, right? It's kind of weird that way, but it's true. If you realize that if I'm looking at something, like let's say I look at a little tiny box of space and I see how small it is, and I'm looking inside it and trying to see how many electrons or exactly what energy is in that box of space, right? Out here, I have a big box of space. In my case, let's say I have a box of, I'll take this jar. Okay, I have a jar, and this jar contains a certain number of particles, and in this particles has a certain amount of particles in it, and that those particles have a certain amount of energy. Okay, that I can measure that. But of course, as you know, the particles are always moving, right? The thermodynamics of PV equals nRT and all that are millions, billions, trillions, quadrillions, quintillions of particles in here. So I can't keep track of every single one, right? But overall, I can measure the amount of energy in here, right? I can measure the amount of energy in here sufficiently precisely that I can get pretty close. I can get to a precision of 1 part in 1,000 or 1 part in 1,000,000 or even 1 part in 1,000,000,000 because there are trillions and quadrillions and quintillions of particles in there, right? So all that extra stuff, if I can't measure it to that precision, no big deal. But folks like Werner Heisenberg later on realized, you know what? If you're now measuring not billions and trillions and quadrillions and quintillions of particles, but just like a few particles, 100 particles, 12 particles, individual particles, the more you look at that, the uncertainty of each particle starts to exceed the total thing that you measure in that particle. So like a particle like an electron has a certain amount of, let's say, energy in it, right? A photon might have a certain amount of energy, but the uncertainty at any given time is large. Whoa. Okay, I don't know if I was able to explain that in a way that satisfies what you're doing here, but let me give an example. Okay, the mathematical aspect of an uncertainty principle might be drawn something like this. This is just one example of how. Okay, let's say a photon, okay, has a certain amount of energy. All right, and so let's say there's an E example. E is the energy in a photon. All right, and that energy of that photon, I can measure how certain that energy is, and I'm going to measure it like right now. But my measurement takes a little bit of time, doesn't it? I have to basically turn on my instrument, measure between a certain time and a certain other time how much energy that photon has, right? So there's amount of time for the measurement. So there's energy and time. So I say that over this period of 1 second, over this period of 1 second, I have my machine on, I'm turning on, and I'm measuring how much energy that photon has, right? This is stuff that you might have been thinking about in some sort of laboratory context when you're in some lab class, like a chemistry lab class or a biology lab class or something like that. You may wind up seeing like you're always trying to measure something, but you know that there's some sort of error involved, right? So E would be the energy of this particle, right? And T is the amount of time you're measuring this particle's energy for. Make sense? Cool. So let's say if over 1 second or something like that, you measure that the energy of this photon is a certain number of joules. Okay, great. Now, if you change it, what's going to happen? Let's say you measure the energy in a certain amount of time. Let's say instead of 1 second, you measure how much energy it has in a tenth of a second. Well, what's interesting is within that tenth of a second, from the beginning of the tenth of the second to the end of the tenth of the second, right? That photon has a certain energy. But inside that tenth of a second, you don't know if the energy has increased or decreased. Make sense? Yeah. Um, Now let's say I measure it for like a hundredth of a second. From the beginning of the hundredth of a second, 0.001 second to 0.01 second to 0.02 second, right? That's a hundredth of a second. I know that from the beginning to the ending, the amount of energy in that photon is a certain amount. But within that hundredth of a second, from like 0.001 to 0.002 second, the energy could have like flip-flopped. Want to go woo, and you wouldn't have noticed it, right? You would have temporarily gone woo, and you wouldn't have noticed it, or it temporarily went like had no energy for a very short time. You couldn't tell what that is. So in other words, the more tightly you measure your time, the more the fluctuation the energy can be. If you measure for like a whole second, then the fluctuation in energy isn't going to be that much. But the more you narrow down the amount of time you measure, the more the fluctuation can happen on a very large scale, and you wouldn't be able to detect it. That is the nature of the uncertainty principle. So if I'm going to write this, okay, so I'm going to write down delta. Remember that delta that we used before? The change in energy, right? If you multiply the amount of change in energy by the amount of change in time, right? I'm going to draw little arrows here and call that change in. And then that one too is also change in. So change in energy times a change in time, right? That has to be a certain amount. And you always are not able to get bigger or smaller than that amount. That amount is always, it's like a limit, right, of what you know. Greater or than about equal to some limited number. All right, what is that number? It has to do with Planck's constant, the thing that you multiply to get the energy of a photon. All right, it's about h. I'll be right back. Hang on just a second. Okay, hold on. Hold on. Be right back. Hi, I'm back. Okay, thanks for your patience. What I just wrote was that the uncertainty principle showed this, right? The energy or the change in energy here, multiply the change in time or the time interval, right, has to be greater than this number h, Planck's constant. So let me write those specific definitions in there so that you know what I'm talking about. Now, there's another version of the uncertainty principle because the multiplication of time and energy is equivalent in many ways to the multiplication of momentum and position, which is something that is also expressed in sort of the same way. So time interval in which you're measuring it, right? That's this thing, delta t, right? So the time interval in which you're measuring it, and then this is the actual energy. So the change in energy and the change in it, you multiply them together, it has to be greater than this h number, which is Planck's constant. Now, this is a simplified version, as I said before, of this uncertainty principle. You don't need to know the exact specific numbers in the derivation because the idea is the point, right? Planck's constant, how big is Planck's constant? It's very, very, very small, right? Let's go back and remember light's equations, right? Here, right? The three equations that we've used before in the past, but that third equation we'll talk about more when we talk about cosmic physics, which is super, super cool. But these equations, remember that the speed of light, right, is the frequency of its light multiplied by its wavelength, and the speed of light is very fast, 3 times 10 to the 8 meters per second in a vacuum. And then the energy of a single photon, right, is E equals h, Planck's constant, times the frequency, in per second, or E equals hc over lambda, right? This f here shows the frequency of this wave, and lambda is the peak to peak length. This is the thing that you've seen before, right? And now what we've done is take this Planck's constant. Well, we didn't do it. Werner Heisenberg did. Took this Planck's constant and then sort of went further and realized that, wow, that Planck's constant is like a limit of our understanding. It's like a way that we can measure our knowledge or our limits of it, right? Which I will write down here what Planck's constant actually is. Where'd that black pen go? Here we go. Okay, so that is, let's see here, 6.63 times 10 to the minus 34 joules times seconds. That's Planck's constant. So that 10 to the minus 34 joules second is really small. But what we're saying is, so take an example. If the time interval were 1 second, right, then the amount of energy change that could happen within that 1 second time interval is 6.63 times 10 to the minus 34 joules, which is a very, very, very small amount, right? It's less than 1 trillionth the amount of energy of a single photon that's coming from that light bulb and hitting me on the cheek right now. Okay, does that make sense? So it's very, very, very small. But if I start measuring time intervals smaller, let's say I go to a millionth of a second, or a billionth of a second, or a trillionth of a second, then that energy starts to increase, right? The amount of energy that could wobble or change in there can get bigger. So if we're talking about little tiny things that are happening on very small fractions of a second, we start not being able to tell the difference between how much energy is in any given spot at any given time, because we're talking very, 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 very small amounts of time. That is the nature of Heisenberg's uncertainty principle. We will get back to that, like I said, in cosmic physics. When you have that uncertainty, you can literally, possibly create an entire universe. Whoa. Okay, never mind that. Let's have that further conversation later. But if you're talking about the uncertainty principle and you have this energy and you have this time, then you start having the different things happening in quantum mechanics, right? A few things are shimmering. I will put the other version of the uncertainty principle as well. All right, example, delta P, that's the momentum that we were talking about before, remember, right? Times delta X, which is the position, right? The uncertainty position is also has to be greater than the H, right? Greater than or equal to H. Now this approximately equal to is not really necessary, but because it's kind of H is bigger than the actual formal limit, I'm putting that in there so that you kind of know, you know what, here's what I'm going to do. Just, you know that there is that in there, but I'm going to mark it off. I'm going to just cross it out. All right. And like that. Like that. Okay. It's going to be greater than H. It could be greater than or equal to H. It could be greater than or about equal to H. But I'm just going to say it's greater, just so you know that it's an uncertainty. All right. So you always know that. If you want to put those little squiggly things in, I'm cool with it. In fact, I encourage you to understand that uncertainty is the whole point, right? There's an uncertainty about it, but it's always going to be greater than that Planck's constant. You know what? I'm going to put it back in. I'm going to put it back in. Greater than approximately equal. Greater than approximately equal. There we go. All right, I'm still going to keep that in there because that uncertainty is necessary, and I want it to be there. Got it? Certain, uncertain. Gee, I'm just not sure. The point is, all of this is uncertain, right? And therein lies this amazing thing about quantum physics. There's another aspect of quantum physics we'll talk about in the next lecture having to do with quantized stuff, right? That's just that energy and particles and stuff like that, our individual particles. But what is the importance of this? I want to explain this to you right away, okay? Because if you have delta P and delta X is always greater than or equal to something, then that means that if I measure the momentum of a particle, right? If I know how fast it's going and in what direction, I actually don't know very exactly where it is at any given time. What? That's right. So you have like little spaces, basically. If I'm looking, if there's a whole bunch of particles and they're all moving around with a certain direction, a certain mass at any given time, or a certain momentum. Remember, photons can have momentum even though they don't have mass. If you have that kind of delta P and delta X, if they got these things moving, then their position is uncertain. At any given time, one particle could be here and the next particle could be there. Next moment could be there. Next moment could be there, right? So it's moving and shimmering. And because it's moving and shimmering that way at the same time, because depending on the time interval, the energy is different. That means that the momentum is going to change. That means that the position is going to change. That means you just have, at any given moment, a particle is highly uncertain. You look in a box, you're like, where is it? Where is it? I don't know where it is. It could be here, it could be there, it could be here, it could be there. Over time, right, if you measure it over a period of a fraction of a second, a hundredth of a second, a whole second, something like that, then you're like, ah, yes, that's the amount of energy it has, that's the momentum it has. But the uncertainty remains. These billions and trillions and quadrillions of particles in this jar, the uncertainty is very low because there are a lot of particles, because it's big, right? But when it's small, the uncertainty can be very comparable, very similar to the actual momentum of the object itself or the actual energy of itself, things like that. So what does that mean? Let me tell you, this is cool, everybody. You ready? If I have a screen of atoms here, okay, and I have an atom here, and I have an atom here, and this atom is coming toward the screen. If the screen is thick enough, right? If it has several atoms in it, it's not gonna be able to get through. That's just what happens if I like shine a beam of light or something at a brick wall, or it's like not gonna go through. But because there's uncertainty in any given moment at any given position, if I send enough electrons or enough photons at some sort of thing that's microscopic, because this thing is literally shimmering, right? Its actual positions is unknown from moment to moment. I might actually be able to get one particle, just the right shimmer moment, poof, pop through the other side. So it's like, poof, right through, poof, right through. If I have a solid piece of material, the uncertainty principle means that every once in a while, I can get another solid item right through it anyway. I can send something through a wall. Whoa, is this possible? This is the theoretical idea that was put forward as, in part, as a result of the uncertainty principle and quantum mechanics in general. Okay, the quantum physics overall suggested that there was a possibility that you could literally tunnel through a wall. Okay, so this is what we call quantum tunneling. The implication of this is quantum tunneling. All right. At this point, if you have watched any of the superhero movies regarding the so-called quantum realm, you're starting to say, wait, this is a little bit out there, or in here, or something like that. Are you telling me that the quantum realm actually exists and then you can like tunnel through space and time and things like that? Well, no. The quantum tunneling that I'm talking about here is real, and it actually happens. And I'll give you an exact example of that very soon. But the idea of like the quantum realm and the laws of physics don't work anymore, right? That's just pseudoscience for entertainment purposes. That's fun stuff, right? You're using quantum words and things like that to say, oh, we can tunnel through here and there and do timelines and blah, 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 right? Yeah. Actually has a scientific backbone to it, which I can talk about, and I will talk about not too long from now. Just realize that there's still a lot of that stuff that's all pretty fake. That whole you as a human being being able to shrink small enough to go into the quantum realm, that's where things fall apart in that particular analogy, right? So can Ant-Man or the Wasp or, who cares, the Hulk go through, the quantum realm by squeezing down and then zipping through and then coming out? No, because if you take yourself, which is a large macroscopic object, and then you turn yourself small, all of your particles are uncertain. And so you as an actual entity no longer exist in the way that you used to. And you can't reassemble yourself and blow yourself back up to reasonable size again, because all your uncertainty will have been imprinted back in. At any given moment, when you're pulling yourself back out, you do not look or think or be the same as you were when you shrunk down. Okay, so don't worry about the quantum realm and the thing. It's fun to think about, and I'm always happy to entertain you. You know, I love science fiction and comic books and stuff like that. So I want you to know that, like, enjoy it. It's like, oh wow, quantum stuff, but know the actual quantum stuff, because actual quantum stuff is even cooler than the fake stuff, right? But enjoy the fake stuff too. I have fun with it. Anyway, there's that my disclaimer about the quantum realm. Okay, so anyway, quantum tunneling actually happens. This has to do with all that quantum mechanical thing, particles as waves and particles, waves as particles, right? Allows this sort of shimmering that happens of particles. And therefore, when other particles try to come through, occasionally they shimmer right through each other. Quantum tunneling. There's also that concept of the flash. You guys ever seen it like vibrating through walls and stuff? No, that does not happen. Let me tell you about that. Okay. When you are vibrating through wall, that's quantum tunneling, you can get through from one barrier to another. But the flash, right, is made up of trillions upon trillions upon trillions of particles, right? The wall is made of trillions upon trillions upon trillions of particles. So maybe you can get a few of the particles, a few dozen or a few hundred particles, or maybe even a few thousand or a few million particles of the flash through the first layer of the wall. But then the second layer of the wall, you got to quantum tunnel through that one too. The next layer and the next and the next. And the odds of quantum tunneling at any given time are so tiny that what basically happened is that the flash tried to vibrate through a wall. What had happened is that part of him would vibrate through the first, millimeter of the wall. And then the next part of him would vibrate through the next millimeter of the wall. And then after about a few millimeters, right, like this much, the flash would be like, believe me, it didn't happen. The rest of the flash would bounce right off. Okay, so don't worry. That kind of thing doesn't happen either. All right. But at the tiny, tiny level, at the microscopic level, it is possible for individual particles to tunnel through barriers that otherwise would seem solid or impenetrable. Okay, at the tiny, tiny level. And this works. I will tell you 2 examples of how this works. Example number 1 is actually in your phone. Okay, it's actually in the computer. In the miniaturized electronics, we're talking about electricity and magnetism, right? In the miniaturized electronics of modern devices like phones and computers, there are these parts inside them. You want to be able to control how much electricity goes through at any given time, right? You have to control it at the very, very detailed microscopic level, at the level of only a few electrons at a time. But remember, those electrons are both particles and waves, and they're uncertain. You're not really sure how individual electrons will work at any given time. But if you design your equipment right, you can create the combination of electric and magnetic fields and the way that electrons flow in them so that you can count on quantum tunneling of electrons, photons, small particles to transfer tiny, tiny little intervals of electric power or light in through these different devices. Okay, there's something called a quantum tunnel diode. All right, quantum tunneling diode, which actually that populates your devices in large numbers. So to this day, if you're like, I remember when I was younger, it's like, no, quantum mechanics can't possibly exist. How is this possible? Right? It doesn't seem to make sense at all to me. And then a friend of mine who is now actually a quantum computing specialist at a major university in this world right now today. I will, not name this person because this person brilliant is awesome, and someday you might want to talk to this person. Okay, that person then basically told me, well, quantum diodes work just fine. So if quantum mechanics doesn't work, then there are a whole lot of quantum diodes in this world that aren't working because of real physics, right? And I'm like, ooh, you're right. So I was chastened. My original ignorance, was put forth on this sort of thing, like, you know what, I should really figure that out. And that helped me understand stuff. So today I think is really cool. Understanding, right, and learning, seeing how this all stuff was built was essential to my sort of realizing that all of this very out of this world seeming kind of hard to understand ridiculous stuff actually is real. We use it every day. So quantum tunneling is, in real terms, I will give example number one. I'll just write that down. Quantum tunnel diodes. I want you to read, right, or watch some videos in devices about quantum tunneling diodes or just quantum mechanics in our daily lives, which is really, really, really cool. Okay, and it's really fun to look at. And then the second part, okay, I want to tell you about this quantum tunneling thing, and we'll kind of wrap up this conversation for now because, oh, there's so much to talk about. It's so beautiful. We're just going to focus on this for this time, okay? If you have a hydrogen atom and a hydrogen atom, so a proton and electron orbiting one another and proton electron orbiting together, you take these two things and you bump them against one another. You smack them against one another, smack, 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 right? They will never come together. Just in our regular world, smack, 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 smack. It will never come together. Why? Because there is this barrier, right, with the individual atom. That electron plus proton thing, that atom, has a quantum mechanical energy barrier, and it has highly repulsive ability. You can't get the protons to smack into one another. Okay? Even if you strip away the electrons and you're got just a proton and a proton, bang, 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 against one another, and you do that for, forever, millions and millions or billions and billions of years, they just won't come together because they'll just bounce off. The electromagnetic repulsion is too strong. The barrier, called the Coulomb barrier, named after this guy Coulomb, just boom, boom, it'll never come together. But remember that a proton is made up of up quarks, right? Two up quarks, a down quark, and a whole bunch of gluons. So they're made up of quantum particles. And so there is a little bit of uncertainty sometimes in where they are and what they do, right? Yes. So if I take this proton, which is this shimmering thing, right, and this proton, which is also a shimmering thing, and I smack them together under the right circumstances, right, they can quantum tunnel. And they can tunnel in such a way that they transform into something else. In fact, this is a very, very, very important activity that happens. You have a hydrogen and a hydrogen, two protons, right, hitting one another in the right circumstances. And then one of the protons will transform because of the quantum tunneling effect into a neutron. And then you have a neutron and a proton stuck together. And that becomes a different kind of hydrogen nucleus. It's called a deuteron or a deuterium nucleus, right? That's nuclear fusion. Yes. So it can happen. Now, that tunneling, like I said, if I do it here, the conditions here on Earth, say today on a nice day, regular room temperature, whatever, with atmospheric pressure, will never happen, right? That quantum tunneling will never occur. But what happened was in the 1930s, a guy named Hans Bethe, all right, B-E-T-H-E, he was a German physicist who had to escape before the Nazis killed him. And he wound up at Cornell University, and he spent his career doing nuclear physics of awesome proportions. As a theorist, he won the Nobel Prize in Physics. And Hans Bethe, he figured out that in conditions that were, say, temperatures of, say, instead of a few hundred degrees Kelvin here on Earth, few million, 10 million Kelvin. Okay, so like 30 degrees Fahrenheit, 30 million degrees Fahrenheit. And if you had pressures that were a billion times, 2 billion times Earth's atmosphere at certain sea level. Okay. And those extreme conditions, if you take two protons and bang them together, on average, over a billion years, there's a 50% chance that you can have a little tiny bit of tunneling. The 50% chance that you take two protons banging against one another for a billion years, they'll actually, under those extreme, 30 million degrees Fahrenheit, 2 billion Earth atmosphere conditions, actually have a fusion happen. and then the two protons come together to make a deuteron. Wow, that's pretty extreme. Doesn't seem very useful, does it? But as it turns out, in the hearts of stars, those are the conditions. So in our sun, nuclear fusion is happening all the time. And that's why the sun shines. And even later on, as we'll talk about it, we humans were able to figure out, so for brief moments, we can create those kinds of very, very unusual extreme conditions and thus produce nuclear fusion in our lives, in our world today. Yeah, pretty cool, right? All right, so that's the other example that I want to write down, another example of quantum mechanics and quantum tunneling in specific happening in our lives, in our world. Nuclear fusion is another example of quantum tunneling. All right, so we've talked about a lot already about the fact that waves and particles have this duality, right? That's the key point here. Wave-particle duality, key aspect of quantum mechanics. And thus, that kind of leads mathematically and logically the idea that there's uncertainty on the quantum mechanical level, right? Particle and a wave, if you're not sure which one it is, a particle wave, you can also not be sure where the energy is in any given interval of time, or where the particle is in location given a certain interval of momentum that you're measuring. And you wind up with things like quantum tunneling. And that produces things like the quantum tunnel diodes, the electronics and devices that we see today, plus nuclear fusion. Is this cool or what? Anyway, these are the things that we'll be talking about. I hope you've been filling out your study guides. There'll be other things to do in the study guides. I can't wait to tell you more about quantum mechanics in the next lecture. It's the best stuff, man. And it is in our lives every single day. Pretty cool. Talk to you later. Thanks.